On August 25, 2012, a machine the size of a small car, built in the 1970s, running on less power than a refrigerator light bulb, crossed a boundary no human object had ever crossed before. Voyager 1 left the solar system, the signal confirming it traveled for 17 hours at the speed of light before reaching Earth. Ed Stone, the mission's lead scientist at Caltech, had spent 35 years waiting for that moment. When the plasma wave data finally resolved, his team knew we had done it. Here is what they found. The edge of our solar system is not a clean line. It is a compressed, asymmetric magnetic bubble, called the heliosphere, being crushed on one side by interstellar wind and stretched on the other into a long tail. The solar system has a shape like a comet. NASA confirmed this using data from its IBEX satellite, published in Nature in 2013. That was not what anyone predicted. For decades, physicists assumed the heliosphere was spherical. A neat, orderly barrier. The real shape is something stranger. Lopsided, dynamic, alive in ways the models never captured. But here is where it gets strange. Voyager 1 crossed the edge, and the sun's magnetic influence followed it. The boundary did not behave like a wall. It behaved like a membrane. Stamatios Krimigas at Johns Hopkins called it a purgatory region. Not quite inside, not quite outside. The particle data showed no single sharp crossing. Just a slow, turbulent negotiation between our star's reach and the galaxy's. The bubble holding back the entire galaxy is messier than we imagined. And it is not holding as firmly as we thought. So how does it actually work? And what happens at the places where it is failing? The sun is not a quiet star. Every second, it hurls 1 million tons of charged particles outward in every direction. A constant invisible storm called the solar wind. That wind doesn't just blow into empty space. It inflates one. Think of it like breath filling a balloon. The solar wind pushes outward against the surrounding galaxy, carving out a vast protected bubble around everything. Every planet, every moon, every spacecraft we have ever launched. That bubble is the heliosphere. The scale is almost offensive to comprehend. The distance from Earth to the Sun is called 1 astronomical unit. The heliosphere stretches 100 of those units before the solar wind finally runs out of force. That is about 15 billion kilometers from the Sun to its first real boundary, called the termination shock, where Voyager 1 crossed in December 2004. But here is what the heliosphere actually does. Galactic cosmic rays, high-energy particles fired by dying stars across the galaxy, constantly hammer the outer edge of this bubble. Without it, those rays would flood the inner solar system far more intensely. The heliosphere absorbs the punishment so the planets don't have to. For decades, scientists assumed the bubble was spherical. Symmetrical, tidy, it made sense on paper. Then in 2009, NASA IBEX satellite, a spacecraft the size of a tire, started mapping the boundary using a completely different method, detecting neutral atoms bouncing back from the edge. What it found stopped researchers cold. The heliosphere is not round. It is compressed and flattened on the side facing the flow of interstellar wind, pushed inward like a thumb pressing into a soap bubble. David McComas, IBEX principal investigator, wrote in the Astrophysical Journal letters that the results do not match any of the previous theoretical models. By 2013, the picture sharpened further. The heliosphere appears to trail off on its opposite side, stretched into an elongated shape, like a crescent, or, as Boston University's Merav Ofer proposed in 2020, something closer to a quasi. Lopsided, asymmetric, alive with turbulence where the two winds collide. That asymmetry is not just a geometric curiosity. If the shield is thinner on one side, cosmic ray exposure across the solar system is uneven in ways scientists are still measuring. Which raises the harder question. If the shape is already wrong, how well does this shield actually hold? On August 25, 2012, 3 instruments aboard Voyager 1 registered something they had never seen before. All at once, the solar wind particles, which had been streaming outward for 35 years, dropped to nearly zero, not gradually. Suddenly, within days, the count fell so sharply that scientists at the Jet Propulsion Laboratory in Pasadena had to check whether the instruments had failed. They hadn't. Galactic cosmic rays, fast particles born in distant supernova and long blocked by the sun's bubble, spiked in the opposite direction. The numbers were almost a mirror image of the solar wind's collapse. One went to zero, the other surged. Don Gurnett at the University of Iowa found the final confirmation. Using plasma wave data triggered by solar eruptions, he measured the density of the material surrounding Voyager. It matched interstellar plasma, not solar plasma. His team published the result in the journal Science in September 2013. Ed Stone, Voyager's project scientist at Caltech since the very beginning, called it one of the most important milestones in the history of exploration, leaving the domain of our sun. But nobody expected what came next. The magnetic field barely changed direction. Scientists had built decades of models predicting the sun's magnetic field and the interstellar magnetic field would meet at nearly a right angle. Perpendicular like 2 roads crossing. They were almost parallel instead. The standard model was simply wrong about that boundary. Stamatios Krimigas at Johns Hopkins had already noted the crossing wasn't a clean line. He called it a purgatory region in Science magazine, neither fully solar nor fully interstellar. If the model was that wrong about the boundary itself, what does it get wrong about everything on the other side? Here is something most people never hear about the heliosphere. It has a tail. The sun moves through the galaxy at 70,000 kilometers per hour. The heliosphere does not hold a perfect sphere. It gets pushed, the side facing our direction of travel gets compressed, squeezed tight against the incoming interstellar wind. The opposite side stretches out behind us, trailing into the dark for billions of kilometers. Scientists call it the heliopause. In 2017, data from NASA IBEX satellite and the Cassini spacecraft, published in Nature Astronomy, confirmed its shape. Long asymmetric, fading at the edges, exactly like a comet dragged across the sky. But here is where it gets strange. That shape is not fixed. The heliosphere breathes. The sun runs on an 11-year activity cycle. Periods of intense solar storms followed by years of relative quiet. During those quiet periods, called solar minimums, the solar wind weakens, the heliosphere shrinks. When it shrinks, the shield thins. A 2022 study in the Astrophysical Journal measured the result directly. During solar minimums, galactic cosmic rays, high-energy particles fired across the galaxy by distant supernova, reach Earth in measurably higher numbers. The thinning is real, it is detectable. Scientists still cannot say with certainty what our shield looked like during solar minimums millions of years ago, or whether it ever failed more dramatically. That uncertainty is not small. Then comes the detail that lands hardest. When Voyager 2 crossed the heliopause in November 2018, its instruments measured the heliosheath, the turbulent outer layer, as noticeably thinner than what Voyager 1 recorded crossing a different region 6 years earlier. 2 probes, 2 paths, 2 different boundaries. The heliosphere is genuinely asymmetric. The weakest side faces the direction we are traveling toward. What that means for everything inside, including us, is exactly what the final chapter is about. Here is the thing that stays with you. A signal leaves a spacecraft smaller than a car, crosses 23 billion kilometers of darkness, and arrives here still carrying data, still answering questions, still going. You are alive right now because a star built you a shield. The heliosphere, that invisible magnetic bubble stretching billions of kilometers in every direction, is not a curiosity. It is the reason complex life on Earth had enough time to evolve. Without it, galactic cosmic rays would pour through our atmosphere at rates that damage DNA and strip away the air itself. The bubble is not decorative. It is structural. We never knew exactly what shape it was until Voyager crossed it. That single spacecraft, launched in 1977 on a rocket burning kerosene and liquid oxygen, is now more than 23 billion kilometers from Earth. According to NASA JPL live tracking, as of 2024, no human built anything that has traveled farther. Nothing else has touched the space between stars. Voyager is still talking. Every signal it sends travels at the speed of light, the fastest anything in the universe can move, and it still takes over 22 hours to reach the antennas on the ground. 22 hours at light speed from something we launched. The scientists at JPL who receive those signals are listening to a place no human will ever visit. They are reading the temperature and density of interstellar space the way a doctor reads a pulse. Steady, careful, certain it still matters. We live inside a bubble we cannot see, generated by a star we cannot touch, drifting through a galaxy that is actively pressing in from every side. That is not a metaphor. That is Tuesday.